So the next method of evaluating limits is called the sandwich theorem. So what does this theorem say? So this theorem says that you have a statement here. If f of x and g of x are two functions, f of x and g of x are two functions, and hx is another function, that is, you have a total of three functions, such that fx is always less than or equal to hx is always less than or equal to gx. So if you have three functions which satisfy the condition that the first function is always less than or equal to the second function is always less than or equal to the third function in certain domain, in some domain, and if limit x tends to a, f of x is same as limit x tends to a, gx is same as some limit L. So if fx and gx as limit x tends to a tend to the same limit, then limit x tends to a, hx will also be equal to f. So this is called the sandwich theorem, where this a has to lie in this domain where this inequality holds good. That is, let us try to understand this theorem using the graph. So assume that we have a function f of x. It says y is equal to f of x. So let us say that I am considering this domain. So from here to here, I am considering this domain. So let us say that within this domain, f of x is always less than or equal to g of x. So I am not really concerned what happens after this, but within this domain, I say that my g of x is always greater than or equal to f of x. This is y is equal to g of x. And at some point a in the domain, both these functions are tending to the same limit. It is limit x tends to a fx, limit x tends to a fx is same as limit x tends to a gx. It is both these functions as x tends to a are tending to the same point. Now if there is another function which is h of x, which is always in between f of x and g of x within this domain, it is always in between them, then what this theorem says is this y is equal to h of x also tends to the same limit L as x tends to a. So this is a very straightforward theorem, because the upper function, upper bound as well as the lower bound are going to the same value. So the function which lies in between them should also go to the same value. So this sandwich theorem will be helpful in finding certain special kinds of limits. So let us look at some examples where sandwich theorem can be used. So let us take a sample question. So you're asked to find limit x tends to 1 fx if fx always lies between 2x square and x times x square plus 1 around this x is equal to 1. Now, what is limit x tends to 1, 2x square? So this is the upper bound, this is the lower bound. If both these functions tend to the same value as x tends to 1, fx, which is in between them, also should go to the same value. So limit x tends to 1, 2x square is straightly equal to 2. And limit x tends to 1, x times x square plus 1 is equal to 1 times 1 plus 1, which is again equal to 2. So limit x tends to 1, 2x square is same as limit x tends to 1, this is equal to 2. Hence, limit x tends to 1, fx should also be equal to 2. Next, we are asked to find limit n tends to infinity, integer part of x plus integer part of 2x plus integer part of 3x plus so on up to integer part of nx by n square. This is the most typical problem that you get in sandwich theorem applicable questions. So here you're given integer parts of different functions in the numerator. So how are we going to use sandwich theorem for this question? Now what I try to do is, I'll try to sandwich this function between two different functions. So we know that integer part of x will always be less than or equal to x, right? Integer part of x will always be less than or equal to x. Again, but this will always be greater than or equal to x minus 1. So integer part of x will never be more than 1 greater than x minus 1. So integer part of x will always lie between x minus 1 and x. Similarly, integer part of 2x always lies between 2x minus 1 and 2x. So as you can, this can be very easily understood from the number line. So assume that you have a number x. So this is the integer before the number. This is the integer after the number. So integer part of x will be equal to this number, right? So this is the integer part of x. This will always lie between x and x minus 1. If x is somewhere here, then x minus 1 will be somewhere here. So the value of integer part of x will always lie between x and x minus 1. So integer part of 2x lies between 2x minus 1 and 2x. Integer part of 3x lies between 3x minus 1 and 3x. So on, integer part of nx lies between nx and nx minus 1. Now what happens if I add all this? So integer part of x plus integer part of 2x plus so on up to integer part of nx always lies between x plus 2x plus 3x so on up to nx. That is n into n plus 1 by 2 times x minus 1 minus 1 minus 1 so on, n times is minus n. And x plus 2x plus 3x up to nx is n times n plus 1 by 2 times x, right? Because 1 plus 2 plus 3 plus so on up to n is n into n plus 1 by 2. Now this function always lies between this number and this number. Now if I divide both of them by n square, so this function always lies between this and this. The given function always lies between this function and this function. Now what I try to do is I'll calculate this limit, I'll calculate this limit. If both are equal, then this also has to be this limit also should be the same number. So what is limit n tends to infinity? So n into n plus 1 by 2 times x, 1 n gets cancelled. There is n plus 1 into x by 2n minus 1 by n is equal to what? So as you can very clearly see, as n tends to infinity, 1 by n goes to 0. And here the highest power is n, here also the highest power is n. So 1 can be neglected. So nx by 2n, n and n gets cancelled, you get x by 2. So the limit is x by 2. Next let us go to this. limit n tends to infinity n times n plus 1 by 2n square times x. Here also, as limit n tends to infinity, only the highest power of n matters. So this 1 can be neglected. So n square x by 2n square and n square gets cancelled. So you're getting x by 2. So this limit is also x by 2. This limit is also x by 2. Hence the value of this limit will also be equal to x by 2. So this is how we use sandwich theorem in questions involving integer part of x. So you just need to remember this result. Integer part of x always lies between x minus 1 and x.